Okay, hello everyone. Our goal for today is to understand what the heck is going on exactly in this slide that I'm looking at right here. So, basically, what we're trying to do is we're trying to figure out if we're given a problem like this, can we answer it? So, the idea is we're calculating the amount of energy required to change 10 grams of solid ice at negative 20 degrees Celsius to gaseous steam at 120 degrees Celsius. Okay, a little hint here, we have to be aware of kilojoules and joules. Okay, as we do this problem, we have to think of kilojoules and joules. Okay, so I'm going to run through this really quickly, and then we're going to take it a little bit slowly. So if there's some part that you don't quite understand as I go over this really quickly, then that's the part you really want to pay attention to as I go through it slowly today. Okay, so first of all, what we have here is we have this phase diagram for water. Okay, and phase diagrams for all materials, all molecules look relatively the same. Okay, we're going to have let's look at the diagram. What does it show at first? So here on the left hand side we have temperature, and on the bottom we have heat added. So basically we're adding heat, and as we add heat, sometimes the temperature changes, sometimes it stays the same, but we're still adding heat at a steady rate. Okay, and we'll talk about why it doesn't change temperature too. So that's what this phase diagram is showing. And again, for all materials, it's pretty much always be the same. I will start with it as a solid. Okay, and you'll see a steady change in temperature all the way till you get to a certain point, and this will be the melting point. So at the melting point, what will happen is the energy going in, the energy being added will no longer go into changing the kinetic energy, but it will go into changing the potential energy. So essentially what's happening as we start in the solid phase, kinetic energy is increasing. We know it's increasing because the temperature is increasing, and kinetic energy and temperature are directly proportional to one another. So as temperature is going up, that means kinetic energy is going up. Okay, then we get into the next part here, between here and here. And what's happening now is that the energy no longer is going into the kinetic part of it. We're not increasing the speed of the particles any longer. What we're doing is we're breaking these forces. So we're breaking these forces that are holding the solid atoms together. We're breaking them. So all the energy is going into breaking these these forces, and we're increasing the potential energy. So the potential energy, therefore, is increasing. Okay. So because we're increasing potential energy and not kinetic, we don't have a temperature change. The temperature stays the same. So we keep adding energy until the temperature changes, or so the temperature stays the same. Eventually, we'll get to a point where all of that all of the solid turns into a liquid. Once we get it all turned into a liquid, then again, the temperature will change. Temperature will start to change again as we go into the liquid phase, and this indicates that the kinetic energy then is arising again. Okay? Again, we'll go all the way until we get to the boiling point. So at this point now we have the boiling point. Okay, now all that liquid, all the energy going into liquid again will be going into changing the potential energy. It will be breaking the bonds even further so that now we don't have a liquid, but we have a gas. Okay, so all the energy goes into changing it into a gas. Okay, eventually it'll all turn into a gas, and we go back again. Now we have it all into one phase of matter, and now the kinetic energy starts to go up again because all of those forces are broken. Okay, now if we're changing kinetic energy, we're going to be using Q equals mc delta T. So if we have a temperature change, that means we're changing kinetic energy. We're using Q equals mc delta T to calculate the amount of energy released or absorbed. In this case, absorbed because we're heating the ice up. Okay. If we don't have a temperature change, we're going to use something called the delta H of fusion and the delta H of vaporization. Each change in state has a different delta H. Okay, this delta H is something called enthalpy. And enthalpy is the same as heat. It's basically the same thing, but enthalpy is the heat content of a system or an object. How much heat does that object contain? Really, we're talking about how much heat energy is in those bonds. How much heat energy is in those bonds, okay? So how much energy is needed to go into it to break those bonds? Okay, same thing here, delta H of vaporization. Okay, so as we go through each one of these steps, you'll see like step one is heating the ice from -20 to 0. So heating it from -20 all the way to its melting point. Okay, and that we're going to use Q equals mc delta T. Okay, now the C for this one is the C of ice. And the C of ice is different from the C of water, which we're going to use in this step here, the C of water. So the C of water here is 4.184. We're very familiar with that one, 4.184 joules per gram degree Celsius. We're familiar with that one. But ice is different. Ice is actually 2.09 joules per gram degree Celsius. So be careful of that, 2.09 instead of 4.184. Okay. Now also be careful because this is in joules. This is in joules. However, when we do the delta H of fusion, this is going to be in kilojoules. Okay, so that's why when I did the Q equals mc delta T for this one, and I got joules, I then converted it to kilojoules by dividing by 1,000. So I divide by 1,000 and I get 0.418. Okay. So again, step one, we're using Q equals mc delta T, -20 to 0 degrees Celsius. That's that first line here, that first diagonal line. Okay, that first diagonal line. Then the second step is this flat line here using the delta H of fusion. So it's just the fusion times the number of grams. And that one is already in kilojoules. The delta H of fusion is 0.333 kilojoules per gram. That's the units for that. Okay, those will be given to you. You won't have to calculate them or anything. These are always given to you. Okay, you don't have to memorize them. Okay. Step three, now we have liquid water. Sorry. We have liquid water. So we're using Q equals mc delta T again. The M is 10, C is 4.184, delta T is 100 minus 0. The reason we're using 100 minus 0 is because we're going to heat it from freezing to boiling. The freezing point to boiling point, 0 to 100. We get this many joules, and we have to divide it by 1,000 to get kilojoules. The next step, we have another flat line here. The flat line indicates no temperature change. So we have delta H of vaporization we're going to use here, times number of grams. The delta H of vaporization, again, you don't have to memorize these numbers. They'll always be given to you, 2.26 grams per, sorry, kilojoules per gram. I'm sorry, it's kilojoules per gram. So 2.26 kilojoules per gram. Okay, multiplied by the number of grams, we get 2.26 kilojoules. Oh, I multiplied that wrong, didn't I? This should be 22.6. 22.6. I'll have to change that because this answer will change then too. Okay. Step 5, heat the system. Sorry, heat the steam from 100 to 150. So now we're again all in one phase of matter. So 100 to 150 is Q equals mc delta T. The mass is 10, C is 1.7. So again, C here for steam is equal to 1.7 joules per gram degree Celsius. So it's a little bit different there. Okay. And then the delta T is we ending at 120. So 120 minus 100. So you get 340 joules. Divide by 1,000. And you get 0.34 kilojoules. Okay. And if you add that up, I don't know what you get exactly because I did it wrong. Because this should be 2.26. This should be 20.6. So that's wrong. So you would add all that up and you get an answer. Okay. So that's what we're going to go over. So let's look at this first. Let's look at a blank phase diagram. Okay, so if you didn't quite get something here. So first of all, let's label the states of matter. So this state of matter here is represented by A. That's a solid. It's the lowest energy. Here is a liquid. They're kind of flowing past one another. And then here is a gas. Okay, if we look at what phase changes are occurring, we go from solid to liquid. The solid to liquid, we call that melting. From liquid to solid, we call that freezing. Okay. From liquid to gas, we call vaporization. And from gas to liquid, we call that condensation. Okay, pretty simple there. So here you go. It's exactly what I just pointed out here. Okay, now in order to go from solid to liquid, we're talking heat of fusion. So heat of fusion means melting. And melting is going to be a positive, right? To go backwards from liquid to solid, so go backwards this way, we call that delta H of solidification. And this is actually a negative. We're going to have to lose energy. So negative. So negative delta H of solidification is equal to the positive heat of fusion. So these are opposite of one another. So just negative, positive, negative. Doesn't matter. Just negative and positive. We can think of the same thing here, heat of vaporization. So heat of vaporization, this is in kilojoules per mole. So you can probably, you're like, why is it different? Well, this is in moles. We looked at it in grams. So it's different if you do moles and grams. So just be aware of that too. That's going to be a factor too later on. So make sure you looking at if it's kilojoules and also if it's in moles or grams. Okay. Now, heat of vaporization, that is going to always be positive. We're adding heat to vaporize something. That's equal to the negative heat, the negative delta H of condensation. Okay, well, what is this? So they're equal but opposite, equal but opposite. Okay. So let's talk about what is this H? What is this H? Well, H is enthalpy. H is equal to enthalpy. And enthalpy is technically I say it's always the heat content of a system. How much heat does the system contain? That's basically what I think it as. Heat and enthalpy are basically the same thing. Essentially, delta H equals Q for most situations, not all situations, but most. Okay, so if you think of heat, you can think of enthalpy. They're kind of the same thing. Okay, so now I say like Q equals MC delta T. Well, Q equals delta H as well. Same, similar kind of thing. Okay, so during a phase change again, there is no temperature change. So there's no temperature change during a phase change. So in order to find out the heat released or absorbed, we cannot use Q equals MC delta T because there's no delta T. Delta T is zero. That would be zero all the time. So instead, we're going to use enthalpy of phase changes. So these are the different ones. For condensing, it's delta H of condensation. Boiling, it's vaporization. Freezing, solidification. Melting, it's fusion. Okay, and again, like I said, they're equal and opposite. So negative delta H of condensation is equal to the positive delta H of vaporization, and same thing for solidification and fusion. Okay, you do have to be aware though. Sometimes they give it in kilojoules per mole or joules per mole. Other times they give it in kilojoules per gram or joules per gram. So just be careful. Be wary. Be wary of units. Be wary of units. So let's look at a really, really simple problem here. So how much energy is required to melt 20 grams of ice? Okay, to melt 20 grams of ice. If it's already at its freezing point, we're going to assume that it's at 0 degrees Celsius already. We have no temperature change. Okay, we're just melting the 20 grams. Okay, so here we're going to use heat of fusion because that's what melting is. Okay, so the heat of fusion of water, or the heat enthalpy of fusion of water. So see, I'll use these terms interchangeably: heat, enthalpy of fusion, heat or enthalpy. Okay, that is 0.33 kilojoules per gram. So we do 0.33 times the number of grams, so 20 grams, and you'll get 6.66 kilojoules. You can ignore this last 6. That shouldn't be. So 6.66 kilojoules will be required to melt 20 grams. So this would be positive because we're adding or putting energy in. Okay, we're adding energy in, we're heating it up. Okay, if it was coming out, if it was being released, if it was freezing, it'd be negative. Okay, so that's pretty much it. I mean, that's it. We look back at this problem again. Looking back at this problem again, we have all the different phases. So the first step, heating the ice from -20 to 0. We have a temperature change, so we can use Q equals mc delta T. Okay, making sure you use the sea of ice. This is the sea of ice here. Okay, for step 2, then we have the liquid going to solid. We have a phase change. There's no change in temperature. So we're going to use that delta H of fusion, which is 0.33. Okay, and that's kilojoules per gram. So we multiply kilojoules per gram, we get kilojoules. Okay. I also forgot to mention, don't forget to change this joules because these are in joules per gram degree Celsius. Don't forget to change that to kilojoules. So divide by 1,000. Get that. Step 3, now everything's a liquid. So using Q equals mc delta T. Step 4, again, we have now a phase change, this time going from liquid to gas. Okay, this number's wrong. I just did the math wrong there, 22.6 kilojoules. And again, that the vaporization is in kilojoules per gram. Okay. Then step 5, the final step here, is doing Q equals mc delta T for the steam. Once everything turns into steam, 100 degrees Celsius to 150. Okay, so do that. Oh, this should be 120. I stole this from another problem, just changing numbers, so this should be 120. Okay, so you get all that. This comes out to 340 joules, divide by 1,000, and you get 0.34. And then you just add all these numbers up to get the total. Okay, hopefully that helps. The worksheet also kind of walks you through that as well. So try to do it the best you can. If you have any questions, make sure you come with them to class on Tuesday. Okay, that is it.